Hello, I'm Saikee, in charge of LG Electronics, Home Appliance and Air Solution R&D Center. I'm honored to be invited as a plenary lecturer to the 13th International Energy Agency Heat Pump Conference. Heat pump is an important technology for global greenhouse gas reduction and carbon neutrality, and is expanding into various fields. To increase the efficiency of the heating and cooling sector, which accounts for 30% of national energy consumption, the industry is also making efforts to apply heat pump technology. Today, I will explain state-of-the-art air source heat pump technology to overcome bottlenecks of the traditional heat pump. Looking at global heating methods, direct combustion using coal, wood, etc. was the main method of heating in the past. And today, gas combustion is still widely used around the world. As you know, fossil fuels are very inefficient and release various harmful gases, including carbon dioxide. To solve these global warming issues, the high efficiency heat pump has been widely applied to heating. The traditional residential heating method in Korea was the ondol, which provides heat directly beneath the flooring. Today, this tradition continues with dominant systems using boilers and central heating. Therefore, there are still just a few cases of residential use of heat pumps in Korea. In response to global warming, countries around the world have established goals for reducing greenhouse gases. There are two types of reduction targets. One is an absolute target that sets a target relative to the base year's emissions. And the other is an intensity target that sets a target based on the emissions per unit of GDP. The Republic of Korea also announced its 2050 carbon neutral plan for the first time on October 28, 2020. And we also set specific reduction targets for each sector by 2030. Heat pump will play a big role in reducing greenhouse gases, especially in building HVAC and industrial heat treatment. Comparing to greenhouse gas emissions according to the heating method, when a gas boiler is 100%, the heat pump is 35%, which is significantly lower than conventional heating methods. Therefore, the application of heat pump should be further expanded in line with global energy saving and low carbon policies. Let me briefly summarize the technology and major governmental policies to encourage expansion in heat pump usage. Since the introduction of air source heat pumps in 1927, residential split heat pumps made their advent into the market in 1971. After 1981, efficiency and driving ranges improved dramatically with inverter technology. Since then, its application expanded to large capacity commercial use in 1982 in Japan, residential air-to-water heat pumps in 2005 in the EU, and low ambient heat pumps in 2014 in the US. Along with these technology developments, many countries have been preparing various policies to encourage high-efficiency products so that heat pumps can be widely adopted in the market. For example, Japan has been including heat pumps in renewable energy initiatives since 2003, and the EU has implemented the similar incentives since 2007. Korea, meanwhile, has included ground and water source heat pumps into its national green energy strategy roadmap since 2011. In China, The coal to electricity program was launched to convert fossil fuels into electricity since 2015. Also, several states in the US have been running energy efficiency rebates for heat pump water heaters since 2016. Thanks to these global national policies, the heat pump market will continue to expand more and more in the future. Meanwhile, there are still some fundamental bottlenecks to solve with air source heat pumps. First, heating performance decreases at low ambient temperature. Even when the temperature falls below minus 30 degrees Celsius, operation cannot be guaranteed. Consequently, these are difficult to use as a main heating system in very cold regions, and an additional heating source is required. Second, when continuous heating stops during the defrosting of the outdoor heat exchanger, it may cause discomfort for occupants due to temperature fluctuation and noise. Despite numerous advantages, these problems negatively impact attempts to expand usage of air source heat pumps. Various technologies are under research and development to overcome these issues. I will explain current trends in cutting-edge technology development. In order to improve the heating performance at low ambient temperature, a technology to increase the high pressure of the system is required. To this end, the pressure ratio limit of the compressor must be expanded. The pressure ratio limit of compressors applied to most heat pumps is up to 8 to 10. And in this case, sufficient heating can be supplied at minus 10 to minus 15 degrees Celsius. If the maximum pressure ratio is raised to 15, it will be possible to supply sufficient heating even at minus 20 to minus 25 degrees Celsius. And if it is raised to 20, sufficient heating will be available even below minus 30 degrees Celsius. There are some key technologies to make this possible. First, in order to expand the pressure ratio, there is technology to increase compressor strength and two-stage cycle technology that operates compressors in series. Second is high heating capacity cycle. It includes high power inverter, refrigerant injection cycle, optimal refrigerant quantity control, and optimal heat exchanger design. Third is oil reliability enhancement technology. At low ambient temperature, is required due to increased risks such as oil discharge, oil viscosity, and phase separation with refrigerant. From now on, I will take a closer look at the current and target level of each technology I just described. First, let me explain about compressors. Compressor capacity and pressure ratio needs to be expanded in order to improve the heating capacity at low ambient temperatures. The compressor capacity has almost doubled in the same frame over the past 10 years, and the maximum pressure ratio has increased to 10. If the pressure ratio, which is currently stagnant at 10, is increased to 15, sufficient heating will be possible even at minus 20 degrees Celsius. Pressure ratios in the 15 range are anticipated within the next 5 years or so. In order to create a high pressure ratio at low temperatures, high heating capacity compressor must be prioritized. In the case of scroll compressors, to secure operational reliability even at high pressure ratios, the back pressure structure design must be advanced. In addition, new materials for improving durability and low noise and vibration design under high speed and high compression ratio conditions must be combined. Next is inverter. In order to increase the heating capacity, the high power inverter needs to be driven at high speeds. Therefore, an inverter driving control capable of operating the compressor at high speed is required. Also, high efficiency control can improve efficiency. And a heat radiation design is required due to the increase in the circuit temperature during high-speed operation. The inverter driving frequency has increased from 90 Hz to 165 Hz from 2005 to 2015. And the efficiency has improved from 96% to 98.5% in the same period. High efficiency control of voltage and current is required in the high-speed rotation range of the inverter. As the amount of heat radiation increases due to high speed and high power, cooling technology using refrigerant pipe is applied to increase the amount of cooling in a small area. Refrigerant injection is another effective technology that can increase the amount of refrigerant circulation at low ambient temperature. It shows the available maximum condensing temperature of an air-to-water heat pump. In general, the condensing temperature that can replace the boiler is up to 80 degrees Celsius. The cascade cycle or natural refrigerants such as carbon dioxide can be used, but the system is complex and expensive. On the other hand, the injection cycle using R410A or R32 can be raised to 6 to 70 degrees Celsius with a single cycle. Therefore, it's widely used as a high heating technology at low temperatures. Refrigerant injection injects medium pressure gas or gas liquid mixed refrigerant into the middle of the compressor. As a result, heating capacity increases by more than 20% and the efficiency by 5%. It can also be used to protect the discharge temperature of the compressor, which can rise with high-speed rotation. Recently, double injection, which injects refrigerant once more into the middle stage, has been introduced, which further improves heating performance by about 10% compared to the conventional injection. The amount of refrigerant is also one of the important factors in maintaining heating power. The lower the ambient temperature, the higher the optimum amount of refrigerant needed for heating. If a large quantity of refrigerant is charged primarily for heating, cooling performance may deteriorate due to an excessive high pressure increase. Therefore, if you can control the amount of refrigerant, heating and cooling performance can be enhanced at the same time. It shows the optimal amount of refrigerant depending on the outside temperature. As the outside temperature decreases, the optimal amount of refrigerant decreases for cooling and increases for heating. The difference between the two ranges from 20 to 30%. In fact, in many fields, refrigerant is filled on a cooling basis, limiting the heating performance. Recently, active refrigerant control was introduced. It controls the optimum amount of circulating refrigerant in the system by storing or discharging refrigerant through valve control. As a result, about 20% of the refrigerant can be additionally sealed, improving heating performance at low ambient temperature by 10%. Heat exchangers are one of the key components that determine system performance. It shows the optimum efficiency points for heating and cooling according to the number of heat exchanger paths. Heating performance clearly improves as the number of heat exchanger paths increases. In other words, the optimal number of heat exchanger paths for heating is greater than for cooling. However, the heat exchanger was primarily designed to optimize heating performance, so the cooling performance is slightly degraded. To solve this problem, the active variable heat exchanger was introduced. During cooling, the refrigerant from the upper outlet of the heat exchanger is re-injected to the bottom. Then it creates an effect similar to reducing the number of cooling paths. This enables the implementation of an optimized path for both cooling and heating with a single heat exchanger. Proper oil management is required to reduce mechanical friction inside the compressor. However, oil viscosity is a big problem at low ambient temperature, and oil discharge may increase due to high-speed rotation of the compressor, which may lead to oil shortage. It shows the oil miscibility of R32 refrigerant. Below minus 15 degrees Celsius, both PVE and POE oils can be phase separated from refrigerant, which may cause difficulties in supplying oil for lubrication. Various technologies are being introduced. One technology involves the installation of an oil level sensor inside the compressor to determine the presence of oil in real time. This not only ensures oil reliability, but also improves system efficiency by recovering the oil when needed. Another approach involves oil recovery technology using a small oil pump. When recovering oil from an oil separator, the conventional method causes a loss by gas leakage from high to low pressure. However, the oil pump can directly recover the oil from high to high pressure, eliminating bypass loss. These technologies are taking system quality to the next level by enhancing oil reliability at low ambient temperature. Periodic heating interruption caused by defrosting is one of the major disadvantages of the air source heat pump. To solve this problem, let's take a brief look at the split defrosting. The air source heat pump must be defrosted to maintain system performance in a low temperature and high humidity environment. However, while the defrost operation is in progress, the heating operation is interrupted, inconveniencing users. Various technologies for continuous heating during defrost are summarized. The hydrophobic or the corrugate fin-shaped heat exchanger are designed to delay frost as much as possible, but can lead to poor heat exchange. Hot gas bypass is simple, but defrosting and heating performance are both degraded. And there are systems that use engine waste heat sources, such as GHP, or have a built-in heat storage tank or heater to raise the refrigerant temperature. However, these are very expensive to apply widely. The split defrosting is one of the most effective methods to ensure defrost effectiveness. The split defrost is a method of defrosting heat exchanger alternately by dividing the heat exchanger into two parts. Of course, the size of the evaporator and heating capacity can be reduced by around 50%. But it's possible to supply more or less continuous heating while eliminating cold indoor drafts at relatively low cost. The perfect product concept is to provide continuous heating without defrosting from the air source heat pump. The next topic I'd like to cover is application of heat pumps. The heat recovery technology can supply cooling, heating, and hot water at the same time utilizing waste heat. Also, when connecting a heat recovery ventilation such as DOAS, the evaporator and condenser can be simultaneously packaged in a single unit. In this case, the existing heater can be replaced with a condenser, which is very advantageous in terms of installation and efficiency. Heat pumps are also widely applied to home appliances. Recently, customer demand for clothes dryers have been increasing due to declining air quality from pollutants such as fine dust. Cloth dryers are classified into three types, that is gas, heater, and heat pump. The heat pump dryer takes a little longer time to dry compared to gas or heater models, but it is easy to install, uses over 70% less energy compared to heaters, and provides delicate fabric care at temperatures around 60 degrees Celsius. Looking at the share of use by dryer type, North America has been using gas and heater dryer for a long time. So the use of heat pump dryers there is very limited at 2%. However, the market share for heat pump dryers in Italy, the Czech Republic, and Finland is at 99% and 100% in Korea. Heat pump technology is also applied to clothing care appliances used for styling and hygiene. For example, the styler enables users to easily care for everyday clothing. By applying an inverter heat pump, it's possible to care for clothes without damaging the fabric with an air temperature around 60 degrees Celsius. And because it's 50% more efficient than a heater, you can care for clothes every day without worrying about electricity cost. To summarize what I have shared today, the heat pump represents the most efficient alternative to gas, oil, and electric systems because it saves energy and reduces greenhouse gas emissions while greatly improving the comfort of users. Performance degradation and discontinuous heating at low external temperatures are the challenges that heat pumps must overcome in the future. As the most promising alternative, the heat pump will be used in a wider variety of applications, such as home appliances and industrial applications. Okay, I'm going to finish my presentation now. Despite COVID-19, I'm very happy to be able to meet you online. Once again, thank you for giving me this opportunity. Thank you.